All right. So today's lecture is going to be sort of smooth. I'll just talk about many things. There's not much technical stuff, so hopefully you can just sit back and enjoy. Yeah, I'll be talking about some new language models. And before that, let's talk about the course logistics as of right now. Everything is pretty much the same. We have another tutorial this Friday with the head TA. And then assignment 3 will be released one day after assignment 2 due date, which is March 10th. And as usual, this is a link to lecture feedback. If you have any feedback for me to improve, then that's always very much appreciated. All right. So today, as I said, that it's going to be a very non-technical sort of talk where I'll be covering some new emergence NLM architectures. Now, as you may know that given the number of neural language models out there and more coming out almost every day, it's impossible for us to talk about even 5% of all the different models. But what I'll do is that I'll talk about some of the main ones and with architectural caveats. So first, I'll talk about, we've all seen the transformer architecture from previous lecture. And today, I'm going to give one example of encoder-only model, and then encoder-decoder-only model. And I know everyone wants to hear about ChatGPT these days, but I won't be covering ChatGPT today, but I'll be glossing over the GPT architecture and models. And there's one lecture entirely dedicated for ChatGPT and InstructGPT and human feedback-based reinforcement learning. At the end, Zining will cover it. And then I want to talk about token-free models, which, in my opinion, is an exciting research direction. And we'll talk about why or what is the need for them, and one selective example of such a model, how it works. Lastly, I'll talk about the trends in neural language models, some of the scaling laws, and briefly talk about some of the ethical questions that we as computer scientists or upcoming leaders, you should be aware of and think about it. All right, so to start off, I wanted to share this fairly old snapshot now of the leaderboard of GLUE benchmark. And essentially, the GLUE benchmark is you have an assorted list of downstream NLP tasks, and then you test the efficacy of your models against each of these tasks, and you have a unified average score to tell you how well your model performs against these downstream tasks. And as you can see that even in this fairly old snapshot, the neural language models are handily beating human baselines. So this gives you an idea that even when the baselines are made harder, it's usually there's only a matter of time before neural language models actually solve those tasks better or at human level. So I want to talk about BART, which is a pivotal landmark neural language model that has become an ubiquitous baseline in NLP tasks. It is conceptually simple, multi-layer, and it's a bidirectional transformer and empirically very powerful. So when you think about BART, think about the transformer architecture, and then you just cut away the decoder part and just think about the encoder portion of the transformers. So conceptually, it is built on encoder stacks of the transformer architecture. So basically, there's two different training stages. If you think about, we've looked at Elmo before, and we'll look into Open Al GPT. But essentially, BART has bidirectional access to all the input tokens. And if you consider this like a layer of encoder stacks, it's basically like you feed in the input sequence, and it has access to the entire input sequences at a time, and it can do bidirectional attention on all of the input sequence tokens. And then it's basically at the output layer, you have a linear layer that outputs some whatever logits, whatever your task is, and then it trains on those training objectives just using the encoder. We'll take a look at the pre-training objectives in the next slide. Essentially, another advantage is that in Elmo, if you remember that at any time step, we had a backward representation and a forward representation. And then we also did a task-specific weighting in order to get the final representation that performs as well as it does. But in BART, it's task invariant. You can basically train it for any task, and you don't have to do any task-specific training. So how is BART trained? There's two phases. One is, first, it's pre-trained on a large unlabeled data on two supervised tasks and objectives. So for this training objective, how does it happen? So you can think of this as the transformer encoder layer. And what we do is that the final hidden state, in the final layer of hidden state, we slap on another linear layer of outputs that we want to condition it on. So let's say if it's a language modeling task. So what is language modeling? You're given one word, predict the next word, or you're given two words or a window of words, and you predict the next word. So if we're doing language modeling, then what would be, like, what are we predicting? Where our output layer would have basically the size of our output layer would be the size of our vocabulary, because at any point you can output any word in our entire vocabulary. If you have 20,000 English words, so let's say we want to predict, then you have like 20,000, the dimension would be 20,000, and here you normalize it using softmax, and you then basically get the most probable word. And once we do, so we have that pre-training. So what is the objective that we're training? So we use these two objectives called masked language modeling and next sentence prediction. So masked language modeling falls under an umbrella of training objective called denoising objective. What it means is that you mask out certain words in the input, and your prediction task is to predict whatever that word is. So it's similar to like the denoising objective that we have known since the 1950s. It's basically you have a signal where you corrupt the input signal, and then the task becomes to reconstruct the original signal from that corrupted signal. So here, like the masking of words is a sort of like corrupting the input, and then we're trying to predict whatever the input sequence was, and then we're training based on that. Okay. So let's take an example of the pre-training objective. So in a masked language modeling objective, so let's say you have an input, like the man went to the mask and he bought a mask of milk, and the labels are store and gallon. So then our objective becomes, in the pre-training phase, is to predict this masked words, and there's certain in BART, 80% of the target words are masked with the special sequence token mask. 10% are replaced with another word, and the rest 10% is just left as is, so that there's a bias towards the observation. Now, we've seen there are many variants of how we can do this masking. So it could be word masking or word piece, or we can even mask few words, like a span of words. So each of them have their own quirks. But here we're just looking at the vanilla version where we're just masking out the words. And the other task that we have is called the next sentence prediction. So here, you're given two sentences, and then you're trying to predict whether the sentence B follows sentence A. And 50% of the time it's true, and the 50% of the time is a random sentence. Later research we'll look at a few more ablative studies of key findings. Later research finds that this second pre-training objective is not as important. We can actually train on just using denoising objective as well as without this next sentence prediction task. Given the importance of BART, there's been a lot of research done in order to find some of the ablative findings about this model and what can we learn from them. So one of the findings was about the heads. So if you know that in the transformer architecture, we had multiple attention heads. And in the BART base model, I think we have 12 heads. And then one research finds that each of these heads, what do they attend to, has a certain pattern that adheres to linguistic concepts and linguistic, syntactic information that we already know from computational linguistics. So for example, here, the lines, remember attention is just score of the importance score of like, between the tokens. So here, the blue lines, the darker the lines are, the more weight, and the red is used to like emphasize certain patterns. So the figures over here is showing the attention patterns in the heads from like, in the 12 heads, and we can see certain syntactical patterns emerge from the attention patterns of these heads. For example, here in heads 8 to 11, there's more the attention score. There's more attention score on the determiners of a noun, like the language and so you have similar attention patterns in these heads. What about layers? So again, there's multiple stacked layers in the BART architecture, and it was observed that the linear word order and the surface features are captured more by the lower layers, and syntactic information is more prominent in the middle layers, and the semantic and task-specific features are best captured in higher or final layers. Now, one problem, like research on proposed improvements and modifications to BART, both on architectural choices and training methods, is voluminous and ongoing. Like there was a lot of questions, for example, in the previous lecture as well, that what happens if we mask out? Why do we have to mask out 10% of the words? Like keep it changed. What if I change it 20%, or what if we mask like 50% of it? So these are valid questions, and this needs to be studied better. But the problem is, given the size of these models, it's sometimes getting prohibitively expensive for precise systematic ablations to answer those questions. But there's a lot of questions we don't have answers to yet. So I'm gonna talk about a few of the limitations of this model that has been found from the ablative studies. So although BART shows very impressive knowledge, syntactic, semantic, and world knowledge information, but there's certain caveats that was found that it is very weak at or it struggles with. So the first thing, so by world knowledge, what I mean is that, let's say if I ask a question like, Dante was born in, and then mask, and a trained language model should be able to answer me like Florence, or if I say that the year Barack Obama was born in was, and then there's a masked question, and then it should be able to answer this question. So that's the kind of world knowledge that BART is usually good at. But however, it struggles with certain kind of knowledge. For example, like pragmatic inference. What I mean by pragmatic inference is that, let's say if I ask you that, hey, do you have the time? Then you can understand that I'm asking what time of the day it is. I'm not actually asking whether she actually has a watch on her. So things like that, BART struggles with. And it also can guess object affordances and properties. So it knows that people can walk into houses, and then houses are big, but it cannot infer whether houses are bigger than people. So this is kind of reasoning that we humans take for granted, but BART is not very good with it. In terms of semantic knowledge, BART struggles with representation of numbers. It's also very brittle to named entity representation. For example, there is a catastrophic drop in performance in co-reference tasks when the names are replaced. And it's for syntactic knowledge, it does not understand negations and is insensitive to mal-informed input. Findings do suggest that either the syntactic knowledge are incomplete, or it's not needed for solving whatever the downstream task it's trying to solve. So we have looked at this, we've glossed over this slide in an earlier lecture as well. So when I think about the pre-training of BART, now if I told you that, okay, so I've given you a BART model, how can you solve assignment 2 using BART 2? Like how would you perform the task of neural machine translation using BART? Yeah. Oh, okay. Anyone at them? Yeah, sure.
You start using BART or BART?
BART.
BART?
Yes.
We attach a decoder to whatever it is.
Okay, yeah, so think about like BART, what BART is doing is that the pre-training procedure that you're masking out certain words, or like, you have a denoising objective. So you're creating a very rich representation of the input sequence. But if you wanted to, get a translation, you have to slap on some additional components. And that's where sort of BART the model BERT does is that, like, it adds an autoregressive decoder on top of BERT, and that allows it to do downstream NLP tasks like machine translation. So for example, let's say for neural machine translation, we first pre-trained an encoder like the way we just saw, and then we added another autoregressive decoder part, which you are familiar with, like from your seq-to-seq model lecture, that now let's say this is our, this is a translation. As an input, you have your source language, and as an output, you have your target language. And this is autoregressive. See, this S is shifting everything one step, offsetting it by 1, so that it's maintaining the autoregressive property. And you're basically you're using pre-trained BERT as a way of representation, okay? And you can train the overall model end to end by cross-entropy laws that can be back-propagated, like the usual end-to-end training of a neural language model. But as BERT as an architecture, it's not very suited for doing machine translation directly without adding some extra components, right? Okay. Okay, now let's take a look at, since we just looked at encoder-decoder setup with BERT, so let's take a look at another model that uses the encoder-decoder architecture and is considered as one of the foundation models in today's terms. So this is text-to-text transfer transformer. So this has almost exactly the same architecture as a transformer, but the main caveats of this is that it casts all NLP problems as a text-to-text problem. So what that means is that even if it's machine translation, so you can have the machine translation, you can have your input in such a way that you can use a prefix to say that whatever task you're trying to solve, and you have an example of like what the input and output looks like, and you can we'll see an example of machine translation using T5 in the next slide. But let's talk about the high-level main differences. So architecturally, it's identical to the original transformer. However, it draws from systematic ablations and a lot of experiments to find out what are the techniques that works best, and incorporate those in their design or training objectives. And it also uses a very large curated data set called Colossus Clean Crawl Corpus, which they pre-train the language model on. So some distinguishing features is that it's like, everything is task invariant. You pose every problem as a text-to-text problem, and the unsupervised training is conceptually same as MLMs. So if I say span corruption, which is, again, it's the same as masked language model, but instead of masking a word, we're masking sequences of words, so we can call it like span corruption, okay? Now this figure shows the attention mask patterns. And when I say self-attention mask with prefix, what do I mean is this on the very right-hand side, like you see the attention mask over here. Before we get to that, maybe let's talk about the leftmost mask that you have already seen. So this is essentially a self-attention in the encoder of the transformer. So every output sees every input, and there's self-attention, okay? So everyone's clear on this attention mask. Okay, so the next one is like causal attention mask. So this is like an autoregressive mask that you see in the decoder of the transformer, meaning that an output cannot see words that are in the future. So if Y2 can only Y2 can only see the darkened cells here, X1 and X2. Okay, Y3 can observe X1 to X3, just like that. So this is basically like an autoregressive mask. Does that make sense? Okay, so with the prefix, like causal with prefix mask, what we're saying is that we're going to have a part of the input, X1 to X3, available to all at any time step. Everyone can see that. That's that we call the prefix part, and everyone can attend to those prefix part at any time steps. So if I say, the prefix is like translate English to German, okay? So, or this is not 3 words, but I'm just saying that as an example that you have a certain amount that just defined, like that's just kept for defining the task type. And everyone can attend to this, like this is visible, okay? And the autoregressive part starts from after that prefix part. So that is like basically attention mask with prefix. Does that make sense? Okay, let's see an example, okay? So English to German translation, right? So how do we do this with T5, which is the same architecture as Transform is? And let's say you have an input sentence, that is good. So just on the right-hand side, the picture that you see over here is an example of what I mean by span corruption. Okay, so this is exactly the same conceptually is the same thing as masked language modeling, but here instead of like one word, we have a span of words being masked and basically being replaced with a special token. Okay, and then if this is the case, then what is our task? The task is to we're given thank you X, me to your party X, right? And then our targets becomes for inviting and last, and Z is just a special token to signify the end of the separator token, let's say. Okay. So this is actually a denoising objective, and you should be clear that this is conceptually the same as masked language modeling pre-training objective. Does that make sense? Okay. All right, so then what can we do is that let's say we want to train for a language translation task. And then what we'll do is that we will specify the task using a task prefix in purple here. So this translate English to German. And then we have our input sequence, and then this is our target sequence, right? So we concatenate the prefix, the input and the output, and then use that for our training. Okay? And when we want to predict, we sort of, for the prediction task, we feed it the prefix, the translate, whatever the task specification is, and the input, and then we use a special directive to say that just output whatever the target is. And on the right-hand side, you see sort of the attention mechanism for a prefix LM architecture where the attention is being paid the first X1 to X3 has darkened attention patterns showing that the prefix part is can have full access it's being attended to by all the layers and all the input-output tokens. So basically the task specification is visible, but the future is not for example, the prediction task, whatever we're predicting to or translating to is not it's maintaining the autoregressive property, because otherwise if it can see that thus is good, then there's no task here. We have already know that what is the translation is, but the translation part is the job to predict the translation part. Okay, but it's okay for the model to know that this is a translation task, so which is signified by the prefix. So let's say if we change the prefix with another task, let's say it's a classification task instead of translation. It's a simpler example. So the MNLI task, the task is essentially I give you a sentence, and I give you a second sentence, or a hypothesis, and then you're supposed to tell me whether the hypothesis entails does it follow the first sentence, okay? So if I say I hate pigeons, and my hypothesis or someone else's hypothesis is that I'm hostile to pigeons, then it's true, it's entailment. But if I say that I hate pigeons, penguins don't live on deserts, then it's probably neutral, or contradiction doesn't matter, but it's not entailment. So how would you do this? So in this case, you'd use a prefix, MNLI premise, that sort of specifies the task, and then you have the input, and then you have the hypothesis, and this part is the task, or this is the answer, okay, the target. And then the model will predict whether, once you have trained it, it will predict whether it's entailment, neutral, or contradiction. In this case, it's entailment. So that is the basic. The interesting thing here is to see is that how we're posing any NLP downstream task, whether it's translation or whether it's classification, as text-to-text problem. So you can give me any NLP problem, and I can say that, okay, I'm going to formulate it in such a way that it becomes like a text-to-text problem. And we can do that. I can add a prefix to say that, oh, this is the kind of task, and if you see this prefix, then you do this. And the model learns, once you learn the model, we can pose it as a text-to-text problem, okay? Okay, so now let's talk about the OpenAI GPT papers. So on the right-hand side, you can see the 3 papers, and the number of authors sort of gradually increases. And each of these papers builds on the previous paper. There will be a detailed discussion on just the GPT papers on lecture 13, I think. It will be covered by Zaining. And today, I just some high-level architectural nuances. So the GPT-3 is basically GPT-2 with some improvements and modifications, and which is another like improvements and modifications over the original GPT paper. The core architecture is classic language modeling. More than novelty, conceptual novelty, like the GPT papers are great feats of engineering work, in my opinion. So there's nothing like, conceptually like novel, but in order to do what it does, it's definitely a marvelous engineering feat. So it's essentially, this is the language modeling task that you're predicting, what's the word given the previous words. And the original GPT trains on a standard autoregressive language model, language modeling objective, where you have an unsupervised token, a corpus of tokens, and K here is the context window, and then P is modeled using a neural network with parameters theta. And it is a generative model in the sense that you're using transformer, the decoder block of the transformer. So the decoder block of the transformer is predicting one word at a time. So you feed in some input, then it's really good at generating the next token. So that's why it's a very good generative model. And as you remember, then when it first came out, like there's almost like overnight zeitgeist over creating like stories or passages using GPT-3, so, or GPT-2. Okay. So the key architectural differences, we've already alluded to it by now. So both of them, like the underlying block level ideology is the same. GPT uses the decoder portion of the transformer, like decoder stacks of decoders, whereas BART used the encoder portion. And GPT is an autoregressive model, again, meaning that it's going, the context awareness goes from left to right, and it is not allowed to see what's in the future. It only conditions on whatever it has seen in the past. And you can sort of compare that. So this picture shows basically the pictorial depiction of what we're saying. Compare this with the T5 or the BART model, which utilizes both the encoder and decoder stacks. Okay, so all the models that we've seen thus far that uses some kind of segmentation, pre-processing to segment the input, which we call like tokenizer or tokenization. So, it could be word piece, it could be byte pair encoding, it could be subword tokenization, or sentence-based tokenizer. But there's a need for tokenizer before we can, feed it to our model and train our model. But this whole using heuristic tokenization method in today's era of like neural language models feels like component from the bygone era, where we're sort of hand engineering, how we want to segment this, or and it also like does not. So I think one really good research direction is that whether we can let go of this tokenization part and then just basically operate on just input and output on raw input. And this is what token-free models come into play. So token-free models, as the name suggests, it operates on raw text, like bytes or characters directly. And it removes the necessity for any text pre-processing pipelines. Now, what is the challenge? There are many challenges, but one that immediately comes to mind is the length of the input sequence. So if you're going to deal with one character at a time, then you can imagine that like you're having to deal with an input sequence that is much larger than if you consider words as one contiguous input token. And as you know that, like this transformer architecture or attention-based architecture, the cost of attention goes up quadratically with the length of input sequence in most cases. So this is a challenge, and we'll look at a model that tries to circumvent this complexity. But before that, I wanted to talk about some other pitfalls of explicit tokenization. So first, think of the assignment where you have to do like neural machine translation. So for every language that you consider, in order to tokenize at a word level, you have to maintain a vocabulary map, right? because you observe a word and you need to like somehow map it to an ID and back and forth. And just for like, English to French, you have this like, you need French vocab, English vocab. And if you have like 150 languages and you have like, some kind of vocabulary is a must. And this tokenization, there's many heuristics for how do you tokenize. So, but they're still like hand engineered, or they require language specific knowledge. Which isn't our desiderata, because we want this to be like end to end without any human intervention or heuristic approach. We just want to feed it and we want to get whatever we want. So, and also this kind of heuristic string splitting, it does not really capture the full breadth of linguistic morphology, like morphological differences between languages that we've seen in earlier lectures, right? So you could have languages that does not have any white space. How do you define the segmentation boundaries? Or you could have languages that uses punctuation as a word, maybe. So there's morphological differences are so huge. When you're thinking about most of these models and examples that I've seen, they're for related languages where everything makes sense. We're thinking in terms of English, there's white space, let's just like divide it up with the white space, but there's many more nuances to language that we have seen so far. So it makes it it makes it like this tokenization algorithms not ideal. And also remember that if we're using like a BART like model, or usually like we have a pre-trained large language model and then we're fine-tuning it to some downstream tasks, but this fine-tuning stage, you must match whatever the vocabulary mapping was in pre-training in the fine-tuning stage as well. Otherwise, it's not going to match. Okay, so everything's going to fall apart. And yeah, it's brittle to noise or corruption of the input. Like you can have typos or you could have adversarial manipulations. And as soon as you let's say type cat with CTE, or you make a typo, you're losing the vocabulary coverage because your vocabulary map does not have a word CTE or CTA, it only has CAT, so it loses vocabulary coverage. So yeah, so maybe now let's take a look at one example model called CANINE, character architecture with no tokenization in neural encoders. So so think about the efficiency perspective. Let's say if I told you that so CANINE is a large encoder with a deep transformer stack at its core, meaning that architecturally we're not thinking anything new. We're just thinking about how we want to process like the input tokens, okay? So if we want to do it at a character level, think about the efficiency. Let's say English, right? In order to embed any English input, all you need is like, how many Unicode characters do you need? Like you have 26 alphabets, maybe throw in another like 124 buffer, and then we can pretty much cover everything from brackets to whatever, 200 Unicode code points, maybe more than that. But compare that with a vocab size when we use Word, like there's 50,000 words in English. So you can immediately see that how it can be advantageous if we could do it. And around like 150,000 Unicode code points can cover 154 scripts across like 900 languages, right? So it's a huge improvement. Now, what this specific model addresses the con of it, like the input sequence length increases. And in this model, the main novelty is that they address this challenge by doing downsampling. So they take the input sequences characters and they downsample it to reduce the number of sequence length to similar levels as if we had used word tokenizers. They use stride convolutions for downsampling. If you don't know what stride convolution is, it's not important to know for our discussion. But yeah, they use some kind of downsampling, okay? So the three primary components are vocab-free embedding technique, like how do you embed the characters, character level model that can process this character embeddings with down and up sampling, and perform unsupervised masked LLM pre-training on this character level model using variance. So variance, essentially we're still doing that denoising objective. So instead of masking words, now we'll be masking characters, okay? Or maybe span of characters, which we can call subwords. Does that make sense? Yeah.
You mentioned the word level tokenization would be brittle to noise, that typo cause like unknown tokens.
Yeah.
wouldn't this have, wouldn't like typo cause bigger problem in character-based ones? For example, CAT, if we have CA, we might predict T in the next character because give it CA. But if we have CT, it doesn't really.
Yeah, but still, CT is not it still has a valid mapping, right? Because T has a valid mapping, C has a valid mapping. But if it's a word tokenizer, then CT becomes like unknown word, right?
Yeah. So my question is, in this paper, did they show specifically that they are doing better on the noise?
They do show like comparative results on the downstream NLP tasks, but they don't specifically talk about if you have, for example, adversarial type of, it's not discussed, but that's a valid question. That is a good question, and again, there needs to be more ablative studies done. So they focus on more showing that, okay, you can use this and you can still achieve comparable results, and yeah. So this slide is a side, but at a high level, this is what's happening. So this entire thing is, think of it as a composition of this function over here. So you have E. E is the character embedding. So character embeddings is just basically a hash table. So you're given a Unicode code point, and then that translates to certain character, okay? So that's just that. And then you have the character embeddings, and then think of that character embeddings just like a sentence being fed to a local transformer, and that gives us contextual characters, just like we'd get the encoding of contextual words if we're using words. So that's our H init, okay? But what we're doing is that we're taking this character embeddings, H init, and then that is downsampled. Then there's a primary encoder, and then for the answer, we upsample it again. So the encoding, what it does is that so the downsampling, what it does is that it takes that sequence length, and it H prime down is the sequence length of dimension M, which is like a reduced dimension. And then that is basically upsampled, like after the upsampling is done using a convolution between H init and H down. And then this H up is again fed to a single transformer stack, where it just produces the final character representation or the output, okay? Yeah, so basically, yeah, so the local transformer does H init, and then you have a downsampling using strided convolution and a window of R. And then once we get another upsampling, and that is fed to a transformer to get our final output, which is Y sequence. So this is like basically the high level. The main nuance is that you basically use a downsampling and then use that to encode, and then again do an upsampling. That is the main, I think, novelty in this approach. Okay, so you can read the paper for if you want to see that how does it compare to like word tokenizer based language models. But I just wanted to give you that idea of how we can, the direction of going token-free models, and then why is it important, or what are the advantages of it. I want to talk about last few minutes on NLP trends and implications. So now this slide is very cliched. Everyone knows that like the larger, the bigger, the better trend, and but some of the implications, I think it's talked about a lot, but I think it's very important as computer scientists and the future generation of like tech leaders in the space, that you consider the implications and think about it, because it is almost like it is a tragedy of commons. So can I get a raise of hands? Like, how many of you know about the tragedy of commons? Okay, just one. Okay, so the tragedy of commons is like if you have a shared resource, and then something like everyone individually benefits from taking advantage of the shared resource and maybe deteriorating the shared resource, but overall everyone loses, but individually everyone wins sort of situation. So it could be if you're a villager, you're grazing your sheep in a green pasture, and finishing up the green pasture is bad for everyone, but individually your sheep are getting healthier and you're getting richer. The same thing is about environment or oil production and things like that. So so some of these implications is that it's sort of like a tragedy of commons, so it's easy to gloss over, but because who you are, it's very important that you consider this. But the point I'm trying to make is that first I'm going to talk about like, the trend is like, starting with Elmo in 2018, the language models have been going bigger and bigger. And if you ask the question that what is the advantage of scaling it up and can we quantify it, or are there any laws that how does making the language size bigger helps us? So we can try to answer that question. So there was, okay, so yeah, this is another trend model that in here model size is the number of parameters, and yeah, we get it, it's going big. Some of the cons is just a very quick gloss over is that given the size of these models, the computational requirement of like, doing ablative studies or doing research on this is getting prohibitively expensive. So in order to like, it's only in the hands of a few corporations or startups or that have the amount of resources or money to continue to build these models. So, there should be some democratization of compute power so everyone can benefit from it. So second thing is social impact is just one example of the environmental impact, which is a good example of tragedy of commons. So this paper in 2019 sort of shows that training BART from scratch on GPU is roughly equivalent to a trans-American. The carbon footprint is roughly equivalent to a trans-American flight. Now, why is that important? You have to ask yourself that question. Okay, so going back to that question, so what is the thing with scaling? Like, are there any laws that we can come up with that sort of captures that the advantage of making bigger and bigger models? So this paper here does, I think everyone should read it, like scaling laws for neural language models, and it identifies 3 scaling factors, okay? And these factors are very intuitive. I mean, it's not like, we know this already in a way, that the compute, the data set size, and number of model parameters, denoted by C, D, and N, and they have like a parallel relationship. Like the performance is denoted by test loss. And as you can see that on the x-axis, as we increase these parameters, the test loss is like decreasing. So it's the performance gets better if we increase the scaling factors. And some of the key findings, any questions about this slide? Okay, so this one I find very intuitive, like makes sense. Now, how specifically does the relationship hold? So yeah, there are other things like architectural hyperparameters, like what is the depth, how many layers should I stack, or what is the width of a network is not as important as these 3 scale factors in terms of performance. So another thing is that these factors must be scaled in tandem. So you cannot be scaling, you're just increasing the model size, but you're not throwing more data at it, then it's suboptimal, okay? So in order to, unless you, so they improve smoothly when they're not bottlenecked by each other. And out-of-domain generalization basically means that you're training on a set or on a domain or a set of data, and then you're testing the efficacy for a model in out of like unseen data. And this is exclusively, it is signified by the in-distribution validation loss performance, which improves with the scaling factors. So out of generalization do see some improvements with larger models. And sample efficiency on the right-hand side, you can see that image shows that larger, this is the number of tokens processed. So larger models with fewer samples achieve the same performance. So larger models are more sample efficient than small models, reaching the same level of performance with fewer optimization steps and data points. Okay. All right, so lastly, as we progress, there is homogenization of these large language models. This is like a 200-page paper. I don't expect you to read it, but this is sort of, in this slide, I highlight some of the main overarching points about the implications. So if you go to like Hugging Face, or if you go to the model repository, you'll see that there's a few models are being downloaded thousands or millions of times. And why are they being downloaded? I mean, they are downloaded for a variety of many different tasks that these models can help with, right? So you have data from different modalities, right? So it can be applied in vision, it can be applied of course, in NLP. And then you have these foundational models that are pre-trained, and then these models are being used or adopted to a wide range of downstream tasks. And if you look at the downstream tasks, you can see that it impacts every facet of the society or industry or whatever you want to call it. Everyone is using AI, or they're using a foundation model for some task or the other. So that means is that if there's anything, like there's a single point of failure in the sense that if there's any negatives, for example, bias in this pre-trained foundation model that is being permeated to all these different aspects of the society, because the foundation models contain those biases are being propagated down, right? So it's a cascading error that will propagate. And how does that matter? So one thing that I alluded to is that these models, like, not only they require more and more resources, but there's an increasing trend of moat around access. So you'll see that whether that makes you question whether it's open or closed, because you have to access them using, like, it makes sense as corporations would like to monetize their technology, but the more and more closed nature of these foundation models is something that we should be aware of. And some of the implications that it can have, especially like, gap between industry models which are only available to certain companies and startups with a lot of funding, and compared to like community models. And I talked about the democratization of increased computation demands, and one solution was suggested was whether we need a government intervention in order to support compute clusters so that it's available to, like, let's say, research students or other people working on it. Yeah, so that's about all I wanted to talk about in this lecture. So thank you so much for attending.